Hello, this is Lecture 4. Today's lesson is an introduction to the electrocardiogram, and we'll explore its basis by first examining the electrical vectors of the heart throughout the cardiac cycle. I recommend a supplementary reading in Levick, Chapter 5, and here are your learning outcomes. One of the quickest, easiest, least expensive, and most informative tests in the clinic is the electrocardiogram. It was developed about 120 years ago by a Dutch physiologist named Willem Einthoven. And even before then, it was known that electrodes placed on the surface of the chest recorded electrical events that corresponded to the heartbeat. But Einthoven greatly improved the measurement and dubbed it the electrocardiogram, and being Dutch, he spelled it with a K. So even today, it is known either as the electrocardiogram EKG or ECG. Either way is fine. You'll hear it both ways. So the EKG provides information on the excitation state of the heart over time, and it can help identify arrhythmias or the sites of conduction block or the location and extent of myocardial damage, or changes in the relative sizes of the heart chambers. Modern EKGs, like the ones shown here, and like the ones that you'll use in lab, have built-in computer algorithms that can automatically analyze the waveforms and make predictions about pathologies. But that doesn't mean that you will not have to understand the EKG and the electrical events in the heart that give rise to it. Realize, however, that the EKG does not provide any information on the mechanical performance of the heart. A patient may have a perfectly normal EKG, but his heart may still pump poorly. All of you should now be comfortable with the idea of impaling a cell with a slender glass microelectrode and recording changes in the voltage across the cell membrane, as illustrated here. That is a transmembrane potential. Recall that the transmembrane potential in the cardiac myocyte has a resting potential of about minus 70 millivolts, which represents the separation of charge across the plasma membrane. And then it will spontaneously initiate an action potential, which is unusually long, 200 milliseconds, moving from minus 70 to maybe plus 20, and then returning to resting of minus 70. So that is a transmembrane potential. Now consider what would be observed if the same potential were examined from a different perspective between 2 points along the surface of a cardiac muscle cell. So here, this illustration shows a clump of cardiac myocytes, and we have a voltmeter with sensing the difference in potential across 2 electrodes. In this situation, A is located on the surface of one end of a cardiac myocyte, and electrode B is located on the surface of the other end of the myocyte. So if we start with the resting myocyte, the membrane potential at rest, there is no difference in electrical potential between A and B, right? A strip chart recording of this potential would show no deviation from the baseline, which we call isoelectric. So in this case, because the surface is a homogeneous cloud of positive charge, there is no difference between the positive charge between A and B. So if we trigger an action potential in one end of the cell, let's say on the left side here, a wave of depolarization will propagate down that cell. Now electrode B will be positively charged with reference to electrode A, because on the region underneath electrode A, the outside of the cell has become negative with respect to the interior. And the extracellular potential, the surface potential, will be recorded as a positive deflection on our chart recorder. Now the difference in potential between A and B becomes less and less, with most of the fiber has a depolarized negative surface with respect to the right side, which is still polarized with the positive outside. So our chart recording is starting to drop, still positive, B is still positive with respect to A, but the charge separation is declining back toward isoelectric. And when the whole fiber is equally depolarized, the entire surface will be homogeneously negatively charged, and there will be no potential recorded between A and B on the surface. So we return to isoelectric. Okay, now during repolarization, which begins first on the left side here, the membrane reestablishes its polarity with positive on the outside, and now B records a potential which is negative with respect to A. So our strip chart recording drops below isoelectric to record a negative surface potential. And finally, the cell repolarization becomes complete, and the cell returns to its polarized resting state at isoelectric. If you understand the surface potential, then you understand the electrocardiogram, because that's all it is. It is a surface potential recorded between two extracellular electrodes. So here we have a resting cardiac myocyte. The surface has a uniform distribution of positive charges, and as the fiber depolarizes on the right side here, the surface becomes negatively charged. And as excitation spreads, propagates from right to left, we will see an excited zone with a diffuse cloud of negative surface charges behind a resting zone with a diffuse cloud of positive surface charges. Recall that in the region of depolarization, excitation, the muscle fiber will begin to contract. Now, in the heart, the individual muscle fibers are not arranged in neat parallel arrays, nor are they depolarizing at exactly the same time. But we can represent all of the millions of tiny extracellular potentials as one collective voltage with a magnitude and direction in 3D space. And this momentary separation of charge, sometimes described as the electrical landscape of the heart surface, is called the cardiac vector or dipole vector of the heart. The vector is symbolized as an arrow whose length represents the size of the electrical dipole, and the direction always points toward the region of net surface positivity by convention. So the vector represents the average electrical activity of the whole heart at a particular moment in time. Remember that the muscle fibers of the heart and the heart itself are surrounded by a salty fluid, electrolyte, and the ions in this fluid serve as good electrical conductors. And when electrodes are attached to the surface of the skin, a tiny amount of electrical current that is flowing through the heart extends all the way to the skin, where it can be recorded if properly amplified. So the EKG machine is just a highly amplified voltmeter. Suppose we attach two electrodes to the chest. We designate one as the positive pole and the other as the negative pole. The orientation of the two electrodes in three-dimensional space is called the lead axis. So it would be indicated by this arrow here. That is the lead axis. The EKG machine is wired so that a wave of depolarization approaching the positive electrode is recorded as a positive deflection on the strip chart recording. The ability of the electrode to detect the cardiac vector will depend on how closely the lead axis is aligned to that vector. Maximum deflection occurs when the vector is perfectly aligned with the lead axis. So the lead axis actually sees the entire vector. But if the vector is instead angled to the lead axis, a smaller deflection will be recorded because only a portion of the vector is actually seen by the lead axis. In fact, nothing will be recorded if the vector is perpendicular to the lead axis, because no component of this vector is parallel to the lead axis. And finally, if the vector is oriented away from the positive pole toward the negative pole, it will be recorded as a downward deflection. And in this case, it would be maximal because this vector is perfectly parallel to the lead axis. So a very important concept in understanding EKG is that the lead sees only the component of the cardiac vector that is parallel to it. How would the EKG machine record this cardiac vector in this lead axis? Well, that is the component of this cardiac vector which is parallel to this lead. How about if we recorded the same cardiac vector with another lead axis? Let's call this lead 2, and lead 2's positive pole is located down here. In this case, the entire cardiac vector is parallel to this lead axis, and therefore the deflection would be upward, a positive deflection, and it would be maximal. So recall that the excitation does not flow erratically through the myocardium. Rather, it is distributed rapidly by the His-Purkinje conduction system to specific regions in a specific sequence. As depolarization spreads, the electrical vector of the heart shifts in three-dimensional space, and it does so in the following way. Let's look at the cardiac cycle. The first region of the heart to be excited is near the SA node. The excitation spreads through the atrium, and the vector is pointed toward the cloud of positive surface potential, and in this direction shown by this small yellow arrow. So at this point, both atria are fully depolarized. Their surface is uniformly negatively charged. The ventricle remains hyperpolarized, unexcited, and its surface is positively charged. Why isn't there a vector? Because the fibrous skeleton insulates the atria from the ventricle electrically. Next, the AV node transmits the impulse after a significant delay to the His-Purkinje conduction system. As the impulse spreads down the two bundle branches, the first portion of the ventricle to depolarize is the left side of the septum. Now we have a vector pointed downward and to the left. Excitation continues to spread toward the apex. The vector shifts and becomes larger, pointed down toward the left hip. The last portion of the ventricle to depolarize is the left ventricle. So the epicardium of the left ventricle and the upper portion of the left ventricle near the base is the last to depolarize, and the vector shifts toward the left and becomes large because more muscle mass is involved in the depolarization. And the very, very last portion of the ventricle to depolarize is the upper left epicardium. The vector shifts all the way pointed to the left shoulder. And finally, the entire ventricle is uniformly depolarized. There is no vector because of the electrical insulation between the atria and the ventricles. Now this is a little unusual because the first portion of the ventricle to repolarize is the epicardium of the left ventricle. And so you see the electrical vector is still pointed to the left hip. And as the remainder of the ventricle repolarizes, we return to the resting state. So we've gone through one cardiac cycle, and that takes about 1 second. Now notice where the atria repolarize. They repolarize just as the apex is beginning to depolarize. The ventricular apex depolarization and the atria repolarize. So as depolarization spreads through the heart, the electrical vector shifts in three-dimensional space in roughly the same sequence as a golf swing, as I'll show you in a moment. The first portion of the heart to depolarize is the atria, followed by the left side of the septum, followed by the apex, followed by the upper left ventricle, and finally we have ventricular repolarization. So if we look at the shifting cardiac vector during an entire cardiac cycle, it kind of looks like a lousy golf swing. First pointed down to the left ankle, it comes up as the septum depolarizes from left to right, so it shifts up this way, and finally the apex depolarizes, swings back, and the vector continues as the left ventricle continues to depolarize, and it shifts up this way. So like a lousy golf swing. Well, that concludes part 1 of lecture 4. Come on back after a short break for part 2. Thank you for your attention.